Hi, this is Mr. Ferris. I'm going to walk you through lesson 6.2, the rest of it. So you'll need this handout. It's a 2-page stapled handout. You can download it from Canvas or use the one I passed out in class. We're going to start on page 3 and number 7. In number 7, we're going to look at two random variables and see what happens when we add them. What would happen if we looked at the sums of two random variables? Some interesting things happen. First of all, though, we're just going to simply look at two random variables like we have in the past. So we've got a random variable x that's equally likely outcomes of 2, 4, 6, and 8. So if we think of this as a probability distribution, we can think of this as 2, 4, 6, and 8 being equally likely, and then the probabilities of these things then would be 1/4, 1/4, 1/4, 1/4. And so if we were to find the mean and standard deviation the way we've been doing it with random variable tables, we would type in 2, 4, 6, and 8 into list 1. We would type in the frequencies or the probabilities into list 2, and we would do one variable stats on list 1 and list 2. You can do this if you'd like some practice. I would advise that at least for the first one. But you can trust me that the mean would be 5, and the standard deviation is 2.236 and some change. There are some other decimals there. And then the variance. You might remember that variance is simply the square of the standard deviation, but that number for standard deviation is not exact. So here is a little tip for free today. We would like to use that exact number. So when we square it, we get the right variance. So that number, if you actually go through the process of list 1 and list 2 and do one variable stats and calculate the mean and standard deviation, those numbers are stored temporarily in your calculator. If you go to VARs and then statistics, and I don't know if I forget if there's another step in there, you're looking for sigma x, because you might remember that's actually what you looked up to get that number 2.236. If you find sigma x, you can bring that into your home screen and square it. Take sigma x, square it, and you'll get the exact variance, which turns out to be 5. So that standard deviation was actually the square root of 5, but we might not have recognized it. So it's a good thing to be able to go to your VARs command and find these temporarily stored variables, and then you can get far more accuracy. If we do a similar thing then for random variable y, we're going to let y be the outcomes 1, 3, and 5. They're equally likely, and so the probability of these things happening would be 1/3, 1/3, 1/3. If we run this through our calculator, again, list 1 for 1, 3, 5. List 2 would be the probabilities, the frequencies. Turns out that the mean of y is 3, otherwise known as the expected value. Standard deviation is 1.63333 with the 3's repeating. And then if you do that same trick where you look up that number in your calculator, square it exactly, it turns out to be 2 2/3. 8/3 or 2 2/3. So that's all preliminary, just to get the mean and standard deviation variance of the two random variables by themselves. What we're really interested in on this problem is what happens when you add those random variables together. Well, adding random variables simply means what are all the possible things that can happen? Well, you could get a 2 on the first one and 1 on the second, or 2 and 3, or 2 and 5, or 4 and 1, 4 and 3, 4 and 5, 6 and 1, 6 and 3, 6 and 5, 8 and 1, 8 and 3, 8 and 5. There's actually 12 different sums that you can get. And if you make an organized list, the 12 sums that are possible are 3, 5, 7, 5, 7, 9, 7, 9, 11, and 9 and 11 and 13. If you do it in an organized way, there is a pattern. There are 12 equally likely sums possible when you consider adding x and y together. If you put these into list 1, like we've been doing, and then put all the frequencies in list 2, which would simply, it's kind of tedious, but 1/12, 1/12, 1/12, 1/12, 1/12, 1/12, into list 2, and do that same calculation, one variable stats, list 1, list 2, you'll find the mean and standard deviation for the sum. Now, let me just ask you before we get the answer. We're trying to find the mean of the sum of x plus y. The mean of x is 5. The mean of y is 3. Want to take a wild guess on what the mean of x plus y is? If you said 8, you are correct. And you can verify that by doing the calculator method of list 1, list 2, and the one variable stats command. The standard deviation, on the other hand, is not something that you could just do in your head. It's some number like 2.768, ... So this number doesn't seem to come from anywhere. You can't just add the standard deviations because that would be like 3.8 something. So this doesn't seem to have a pattern. The mean certainly is easy because the mean of the sum is just the sum of the means. But it doesn't look like standard deviation has anything going on. So then if you square that number, and again, try to do it without losing any accuracy, it turns out, and this is maybe one of the big surprises of the lesson, it turns out to be 7 2/3, if you get it exactly. If you go back to the variances that we started with, look at what seems to be true. It looks like the variance of the sum is the sum of the variances. That happens to be a principle. That's a truth. That's a theorem. And that's been proven mathematically to be true for all random variables as long as they are independent. It works if the variables are independent. If they're not independent, then this mathematical proof does not really work. They have to be independent random variables. So if you consider these to be maybe dice rolls or something, that would be easy to assume then. So that's the big principle, that there is a shortcut. Next time you add random variables, you really don't even need to use lists at all. You don't need to use list 1 and list 2 because we know the sum can be gotten from the means of the original, and the new variance can be gotten from the original. What's going to be kind of interesting then is the next time we do this, we probably don't want to find the standard deviation first. The next time we do this, because we have this new theorem, we're going to probably find the variance first because that'll be the shortcut, and then what we'll do is we'll take the square root of the variance to work it backward to the standard deviation. If we do it that way, we will not need to use lists or calculators. So it's kind of cool. We've learned another shortcut that will help us to save time. All right, so similarly, if we look at all the possible differences between x and y, we've got 2 minus 1, 2 minus 3, 2 minus 5, 4 minus 1, 4 minus 3, 4 minus 5, 6 minus 1, 6 minus 3, 6 minus 5, 8 minus 1, 8 minus 3, 8 minus 5. If you do that in an organized manner, you get these 12 equally likely differences. 1, negative 1, negative 3. 3, 1, negative 1. 3, 1, what did I do? 3, 1, negative 1. So then 5, 3, 1. And finally 7, 5, and 3. Again, these are all equally likely. We could put these in list 1, and we could put a bunch of 1/12ths in list 2. Do the calculation like we've been doing. But again, I think you might be able to guess the mean of the difference is going to be the difference of the means. 5 minus 3, which is 2. Here's the thing that you might not expect. If you do it on a calculator, it turns out the standard deviation is exactly the same as we got when we added random variables, and that doesn't seem to make sense on the surface, because if the standard deviation is the same, well then of course the variance is going to be the same. So apparently it doesn't really matter whether you're adding or subtracting random variables, you're still going to add variances. So it didn't matter whether we were adding random variables or subtracting random variables, we got the same exact variance and we got the same exact standard deviation. We did get a different mean, however. So to summarize, as long as your variables are independent of each other, if you're adding or subtracting independent random variables, variances add. That's kind of a broad statement, but there's some detail in there that we have to also kind of flesh out. But in essence, you can find the new variance by simply adding the variances of the variables that you're adding together, or subtracting. It works for subtracting as well. One little thing that's kind of cool, if you graphed all those 12 numbers that we got for x plus y, and you graphed all those 12 possibilities for x minus y and did a box plot, the box plots would be perfectly symmetric. And what you would find is the centers are going to be different. One center is 8, one center is 2, but the variation, the range and the standard deviation, the IQR, are all going to be the same no matter whether you're adding or subtracting. So that could kind of verify that, yes, actually the variation is exactly the same no matter if you're adding and getting 8 for the center or subtracting and getting 2 for the center. The variation in the range is exactly the same. So there's your quick lesson 6.2b, and hopefully that gives you the foundation on which you can do lots of cool problems.